So when light, such as light from the sun, is not actually white at all, instead is a composition of all the colors of the rainbow in the form of waves. The individual colors can be seen only when white light passes through an optical prism that separates the waves according to their wavelengths to form a rainbow. Light waves can be represented graphically by the sine function. In this chapter, right, we will we examine trigonometric functions such as the sine function. In this section, we will interpret and create graphs of the sine and cosine functions. Good stuff, good stuff. All right. So graphing sine and cosine functions, all right? Recall that the sine and cosine functions relate real number values to x and y coordinates of a point on the unit circle, right? So what do they look like on a graph on a coordinate plane? Let's start with the sine function. We can create a table of values and use them to sketch a graph, right? So here's our table of values, and it lists some of the values for the sine function on a unit circle, right? So we have 0, pi over 6, remember that's 30 degrees, pi over 4, 45, right? And then we have pi over 3, 60 degrees, pi over 2, 90 degrees, right? And then you have 2 pi over 3, I'm forgetting what that is now. It's 90 plus 30, I believe, something like that. Yeah, all the way up to pi, right? And when you plug in these values into sine, these are the values you get out, right? So think of sine now as your y. You get out 0, half, square root 2 over 2, square root 3 over 2, 1, etc., right? Notice that these numbers repeat itself kind of in a pattern, right? And we're going to talk about that. But before we go further, let me give you guys a look at what this will look like graphically speaking. All right, this looks good, right? So when you plot these points from the table and continue along the x-axis, it gives you the shape of a sine function. So this is what the sine function looks at, right? Some important things to note, right? The sine function begins at 0, right? Hold on one second, right? The sine function begins at 0. So I just want to bring that out right here, all right? And then it goes on for its full period, right? All the way up to 2 pi. Okay. So we did mention the unit circle earlier. So just to show you how these two things represent, I mean how these two things interact with one another. Let me show you. So notice how the sine values are positive between 0 and pi, which correspond to the values of the sine function in quadrants 1 and 2 on the unit circle. And the sine values are negative between pi and 2 pi, which correspond to the values of the sine function in quadrants 3 and 4 on the unit circle. All right. So you see right here, if we were starting at 0, we go up 30 degrees or pi over 6. That's where that first point would be, right? Go up to 45 degrees or pi over 4. That's where the second point would be, etc., right? All the way up to 90, where we reach our apex, right? Our highest point on the sine before it turns around and starts going right back down, right? So this is what plotting the values of the sine function on the graph looks like, right? From the unit circle. All right. Now let's take a similar look at the cosine function. Again, we can create a table of values and use them to sketch a graph. So table 2 lists some of the values for the cosine function on a unit circle. So same idea, right, as before, right? So we have 0, pi over 6, pi over 4, pi over 3, pi over 2, which is 90, etc., all the way up to pi, right? We plug in these points, and these are our output values. All right. Same thing that we've been doing before, right? We're just creating a table of values. That's all we're doing, right? And then once you create that table of values, you just plot the points, right? That's simple. So here we go. All right. So as with the sine function, we can plot the points and create a graph of cosine, right? As we did before, right? So this is the graph of cosine. Something important that I want to note right here is that cosine starts at 1, right? Cosine starts at 1. Just want to point that out. So just to recap, sine started at 0, cosine starts at 1, right? And then it goes through its entire period, right? All the way up into 2 pi. Just want to make a special note, okay? So because we can evaluate the sine and cosine of any real number, both of these functions are defined for all real numbers. By thinking of the sine and cosine values as coordinates of points on a unit circle, it becomes clear that the range of both functions must be the interval from -1 to +1, right? Because remember, our unit circle had a radius of what? A radius of 1, right? So that's the reason why our function must be in an interval from -1 to +1, right? If our radius was 2, then it would be in an interval from -2 to +2, etc., right? So in both graphs, the shape of the graph repeats after 2 pi, which means that the functions are periodic with a period of 2 pi. So a periodic function is a function for which a specific horizontal shift, p, results in the function equal to the original function. So f of x plus p is equal to f of x, right? For all the values of x in the domain of f, right? When this occurs, we can call the smallest such horizontal shift with p greater than 0 the period of the function. So figure 5 is going to show us several periods of the sine and cosine function. So here we go. So this is sine, right? And how do I know this is sine? It starts at 0, right? Forget the fact that the name was there. It starts at 0, right? We go up, we reach our apex at pi over 2. At pi, we're touching the x-axis at 0. We come down to 2 pi over 3, right? Wait, am I right? 3 pi over 2, excuse me, right? And that's when we're at -1. Finish it off at 2 pi, we're back at 0. That's an entire period for sine, right? And then it just repeats. We go back and we do the same thing again, right? We can also go reverse as well. We can go reverse as well. So remember on the unit circle, when we go clockwise, right? First thing first was negative pi over 2 or negative 90, right? So boom, -1, right? Then at negative pi, we're back at 0. And then now at negative 270 or 3 pi, or next, excuse me, -3 pi over 2, boom, right back at the top, right at 1, right? Going all the way back, and then we finish it at -2 pi, right? So that right there is another period, right? Let's talk about cosine. Now, Forget the fact that the name cosine is there. How did I know this is cosine? Because it starts at 1, right? Cosine starts at 1, right? And the same game is true, right? So I'm gonna go from 0 to pi over 2, right? And at pi over 2, I'm touching the x-axis, so the output is 0. Then I go to pi, right? At pi, I'm at -1, right? Think of it as, remember how cosine is the x coordinate on the unit circle, right? So when we're at pi, we're on the left side, so -1, right? All right. So then after that, 3 pi over 2, back at 0, right? And then 2 pi, boom. That's a full period right there, full rotation. And then of course it continues, right? Right, left and right, it continues. This is what makes it periodic function. All right. Good stuff, good stuff, good stuff. All right. Let me just check my battery real quick. All right, so we're good to go. So looking again at the sine and cosine functions on a domain created at the y-axis helps reveal several symmetries, right? As we can see in figure 6, the sine function is symmetric about the origin. Recall from the other trigonometric functions that we determined from a unit circle that the sine function is an odd function because if we plug in a negative value for x, we get out a negative sine value. So now we can clearly see this property on the graph, right? So for example, I'm at let's plug in -pi over 2, right? So sine of -pi over 2, I'm looking right here, is giving me what? -1. That's it. That's it, right? If I plug in -pi into sine, right? -pi into sine, I'm getting 0. So it's still odd, but anything to 0, anything times 0 is 0, right? But you get the idea. I give it a negative input, I'm getting out a negative output, right? So that's what makes sine odd. Now, on the contrary, on the contrary, so figure 7 shows that the cosine function is symmetric about the y-axis. Again, we determined that the cosine function is an even function. And now we can see from the graph that cosine of -x is equal to cosine of x. So when I plug in a negative value for cosine, I get back out a positive value, right? So what's a good example of this? Let's say that I plug in -pi. So cosine of -pi, right? That's going to give me what? -1, right? -1. If I plug in cosine of -2 pi, that's going to give me out what? +1, right? Good stuff, good stuff. I think the pi over 2 was the one I was supposed to say. So if I plug in cosine of -pi over 2, then that's 0. Yeah, that doesn't work. Okay. Either way, let's sum this all up, shall we? So let's talk about the characteristics of sine and cosine functions. So the sine and cosine functions have several distinct characteristics. They are periodic functions with a period of 2 pi. The domain of each function is negative infinity to infinity, and the range is negative 1 to 1, right? One's being included, of course. The graph of y equals sine x is symmetric about the origin because it is an odd function. But the graph of cosine of x is symmetric about the y-axis because it is a even function. All right. Let's take this up a notch. Let's take this up a notch. So we're going to be investigating sinusoidal functions. All right. So as we can see, sine and cosine functions have a regular period and range, right? If we watch ocean waves or ripples on a pond, right, we will see that they resemble the sine or cosine functions. However, they are not necessarily identical, right? Some are taller or longer than others. A function that has the same general shape as a sine or cosine function is known as a sinusoidal function, right? The general forms of the sinusoidal functions are y equals a sine of bx minus c plus d, and y equals a cosine of bx minus c plus d. All right. Now, from our previous knowledge in other sections, we could kind of guess what the C and the D are going to do, right? C is going to shift the graph left or right, depending on the sign. D is going to shift the graph up or down, depending on the sign. But A and B, those are new concepts for us, right? So let's talk about that. Let's talk about that. All right. So first thing you want to do is talk about determining the period of the sinusoidal function, right? So looking at the forms of sinusoidal functions, we can see that they are transformations of the sine and cosine functions. We can use what we know about transformations to determine the period. So in general, right, B is related to the period by P equal to 2 pi over B. If the b is greater than 1, the absolute, excuse me, let me say that again. If the absolute value of b is greater than 1, then the period is less than 2 pi. All right. And the function undergoes a horizontal compression, right? Remember when we squeeze that together. Whereas if the absolute value of b is less than 1, so a fraction, less or negative, right? Right, is less than 1, then the period is greater than 2 pi and the function undergoes a horizontal stretching. So we're stretching it out. So for example, f of x is equal to sine x, right? B here is 1, right? So the period is 2 pi, right? Which we knew. If f of x is equal to sine of 2x, then b here is 2. So the period is pi and the graph is compressed, right? So if f of x is equal to x over 2, then the b is actually 1/2. So the period, right, is 4 pi and the graph is stretched, right? So let's look at how that looks on the graph, right? So our dark blue line is the original, I'm sorry, excuse me. Our orange line is the original sine function, right? We're starting at 0 as usual, right? We come up pi over 2, we're at the top at 1. At pi, we're at 0. At 3 pi over 2, we're at negative 1, and then at 2 pi, we're right back to 0, right? But now let's look at when the b term, right? The b term is greater than 1, right? So positive 2. So now we're being what? Compressed, right? We're being compressed. So look, we're still starting at 0. We go up, right? And then when we're at we think what that could be, 45 degrees. 45 degrees, right? That's we're at our peak right there. Then at pi over 2, right? Pi over 2 right here, then we're at 0. Then go a little bit further in. That's going to be 135 degrees. Boom. We're at our -1, and then at pi, we're at 0. So this right here, for sine of 2 pi, this is actually a full period right here when we get to pi. And if we're going to extend it out to 2 pi, we're actually going to complete 2 periods. Right there, right? And the reason for that, we've been compressed, right? Let's talk about our turquoise one, right? So this is where our B term is 1/2, right? That's right up here. So now we have been what? Stretched, right? So essentially, we have to go through 2 cycles, right? Just to complete a full period, right? So we start off at 0, right? We reach our apex at pi, right? And then just by when we get to 2 pi, we're only just now completing half of our journey because we just hit back the x-axis at 0, right? When we get to 3 pi over 2, right? If we were to continue this on, right? Let me continue this on a little. I'm sorry about that. Right, if I was to continue this on, right? So right here, just kind of making it up a little bit, right? Right here would be our 3 pi. Oh, no, no, no. Right here would be 3 pi, excuse me. Right here is just -1. And then finally, right here, this would be our 4 pi. So we're going to write that 4 pi. And that would be the entire period for when B, this is when B is less than 1. Let me be more specific. The absolute value of P is less than 1. Okay. So a period of sinusoidal functions. If we let C equals 0 and D equals 0 in the general form, right, equations of sine and cosine functions, we obtain the form y equals a sine bx and y equals a cosine bx. The period is 2 pi divided by the absolute value of b, right? That's our period. I just want to look at an example real quick before we move on. Let me keep that up there just so make it a little bit easier. All right, so we want to identify the period of a sine or cosine function. For example, let's determine the period of this function. F of x is equal to sine of pi over 6x, right? So very simply, my period, right, will be equal to what? 2 pi over the absolute value of b. So that being said, for this particular function, the period is going to be 2 pi divided by what? The absolute value of pi over 6, right? Absolute value of pi over 6 is just going to leave us with positive pi over 6. So now I have 2 pi over 6. And I'm sorry, that should be 6, right? After that, what are we going to do? Keep change flip, right? Keep change flip. Remember, the top is actually a fraction. So the top looks like 2 pi over 1 over pi over 6. That's how this is really looking. So keep change flip. I'm going to keep the top fraction, 2 pi over 1. I'm going to change the division to multiplication, right? And I'm going to flip the denominator to give me 6 over pi Multiplying straight across, pi and pi will cancel. 2 times 6, this becomes 12, right? This is my period. Okay. And long story short, that's how you find the period. Now I'm going to give you a problem to try, all right? At this point, you can pause the video for a second, right? Try it out and then click play again to view the answer. The question is determine the period of a function g of x is equal to cosine x over 3. You may pause now. Okay, so now let's look at the answer. All right, so I have g of x is equal to cosine x over 3, right? So my period is equal to 2 pi over the absolute value of b, right? In this case, right, my b is 1/3, right? B is equal to 1/3 in this case, right? So I have what? 2 pi over the absolute value of 1/3, right? And the absolute value of 1/3, we all know, is just 1/3. So this becomes what? 2 pi over 1 divided by 1 over 3. And then same thing as before, keep change flip. So what do I have? I have 2 pi over 1 times 3 over 1. Multiplying straight across, what do I have? 6 pi. This is my period. Okay. So now I want to talk about the A, right? So we talked about B. Now let's talk about A. All right. So determining the amplitude, right, for the functions, right? So returning to the general form for a sinusoidal function, we have analyzed how the variable b relates to the period. Now, let's turn to the variable a so we can analyze how it is related to the amplitude, right? Or the greatest distance from rest. So a represents the vertical stretch factor, and its absolute value of a is the amplitude. The local minima will be a distance, the absolute value of A, above the horizontal midline of the graph, right? Which is the line y equals d, right? Because d is equal to 0 in this case, right? Remember, d is going to shift that graph up or down, so it's equal to 0 in this case, right? The midline is the x-axis. The local minima will be the same distance from the midline. So if the absolute value of A, right, is greater than 1, then the function is stretched. So for example, let's say that the amplitude of f of x is equal to 4 sine x is twice the amplitude of f of x is equal to 2 sine x, right? So if the absolute value of A is less than 1, the function is compressed, right? Like we're squeezing it down, right? So figure 9 is going to show us several ones, right? So our dark blue line right here is our original sine function, as you can see, right? Going left and right. But let's say that our amplitude was 2, right? So that means that our highest point now is higher. Instead of it going up to 1, it's now going up to 2 in orange, right? You see that? And also correspondingly, we're going down to -2, right? That's our amplitude right there, right? Let's say we increase the amplitude one more time by 3. So now instead of going from 0 to 1, we're going from 0 to 3, right? So you can see how we're stretching, right? And then, of course, if the A was less than 1, right, then we would be compressed, right? We would have a smaller graph, right? Probably one of the benefits of drawing this or playing with the window function on your calculator, this will make it easier to view a stretched or compressed function. All right. Real quick, I just want to summarize this up a little bit. Here we go. So the amplitude of the sinusoidal function, excuse me. If we let C equal 0 and D equals 0 in the general form equations of the sine and cosine functions, we obtain the forms y equals a sine bx and y equals a cosine bx. The amplitude is the absolute value of a, which is the vertical height from the midline. So in addition, note in the example that the amplitude, right, which is the absolute value of A, is equal to half of the maximum value minus the minimum value, right? That's that. I just want to keep this up right here. So I just want to look at an example real quick. Okay. So I'm identifying the amplitude of a sine or cosine function. So what is the amplitude of the sinusoidal function f of x is equal to -4 sine x? And is the function stretched or compressed vertically? All right. Well, let's take a look. Let's take a look. So the absolute value, right, of negative, oh, excuse me, let me take a step back, right? The amplitude, right, is equal to the absolute value of a. That's our amplitude formula, right? So what I want to do, right, is I want to know what is the absolute value of -4, right? Because -4 in this case is my amplitude. Absolute value of -4 is, of course, +4. So +4 is my amplitude, right? This is my amplitude, right? Box it up so we know that that's the answer. And then the next question, is this function stretched or compressed, right? Well, we go back up here, right? And we see, right? Let me just go back up here for a second. We see that whenever a is less than 1, the absolute value of a, excuse me, is less than 1, we have a compression. But whenever the absolute value of a is greater than 1, we have a stretch, right? So in this case, we have what? 4, right? 4 is our amplitude. So this graph is going to be what? Stretched, right? So graph is stretched. There we go. Oh, vertically as well. I mean, let me say that as well. Vertically. Yeah, let me add that little tidbit. Okay. Just want to make a little special note real quick. There we go. So the negative value of a results in the reflection across the x-axis of the sine function as shown. All right. So boom. So remember, sine usually, the sine would start at 0 and then boom, we go up to whatever the apex is, then we come back down. But notice we went from 0 to -4, right? What could have caused that? It's because a is -4, right? So we're reflecting about the x-axis. So instead of going up first, we're actually going down first. Okay. Sorry about that. Let me give you guys an example, right? So our example says, what is the amplitude of the sinusoidal function f of x is equal to 1/2 sine of x? And is this function stretched or compressed vertically? You may pause the video now, all right? And then you can try it on a piece of paper. And then when you're done, you just come back and click play, and then we'll see what the answer is. Let me give you guys a minute to pause. All right, let's take a look at what that answer is. So, right, I have what? F of x is equal to 1/2 sine of x. So my amplitude, remember, that formula is the absolute value of a. In our case, that's going to be what? The absolute value of 1/2, right? And the absolute value of 1/2 is what? 1/2, right? Or positive 1/2, right? So this is my amplitude. I'm just going to write amp for short, all right? And then I want to know, is this function stretched or graph? Oh, excuse me, is this function stretched or compressed vertically? Sorry about that, right? So we saw in our last example that when we had a number, an amplitude that was greater than one, we got what? Stretched, right? So because my amplitude here is less than one, right? We're gonna get what? Compressed. So graph is compressed vertically. Just box that in because that's your answer. Okay. So far, so good. All right, let's talk about analyzing graphs of variations of the y equals sine x and y equals cosine x, right? So now that we understand how a and b relate to the general form equation for the sine and cosine functions, we will explore the variables c and d. So recall the general form y equals a sine of bx minus c plus d and y equals a cosine of bx minus c plus d, right? Or we can also say y is equal to a sine of b times x minus c over b plus d. And we could say y equals a cosine of b times x minus c over b plus d. All right. These are our general form questions, equations, excuse me. Okay. So the value C over B for a sinusoidal function is called the phase shift or the horizontal displacement of the basic sine or cosine function. If C is greater than zero, the graph shifts to the right. And if C is less than zero, the graph shifts to the left, right? A little bit different than what we thought. So the greater the value of the absolute value of C, the more the graph is shifted. All right. So this figure is going to show you the graph of f of x is equal to sine of pi minus, excuse me, of x minus pi. And this is going to shift to the right by pi units, right? Which is more than we see in the graph. F of x is equal to sine of x minus pi over 4. So which shifts the graph to the right by pi over 4 units. So let's take a look. Let's take a look. Let's take a look. Our dark blue line is f of x is equal to sine x. This is our original function, right? That's our original function right there, right? That's a whole period for it. Now, let's take a look at the turquoise color, right? Which is sine is equal, excuse me, f of x is equal to sine of x minus pi, right? Sine of x minus pi. So what happened here, right? What happened here? We got shifted, right? We got shifted where? To the right by pi units, right? So that means that where pi is right here, this used to be 0 over here. Now this is it, right? So negative pi got shifted over to 0, 0 got shifted to pi, etc. Right? Let's look at our orange one. We have sine of x minus pi over 4. So what happened here, right? So again, we always started at 0, but for the orange one, right, we're being shifted to the right, pi over 4. So we move over just like a little half spot, half step, right? Boom. So now where are we starting at? We're starting at pi over 4. And then we go up and down, complete the curve, so to speak, right? We're going to complete the curve. And then that's it. That's it. Let's move on. Okay, so while C relates to the horizontal shift, D indicates the vertical shift from the midline in a general formula for a sinusoidal function. So if you look at this figure right here, y is equal to cosine x plus d has a midline at y equals d, right? So I'm adding a number to the function. So it's going to affect the overall function, f of x, right? It's shifting my graph up by d, right? It's positive, d is positive, so it's shifting my graph up by d. And if d was negative, it would shift my graph down by whatever d would be. Okay. So any value of d other than 0 shifts the graph up or down. So this figure compares f of x is equal to sine x with f of x is equal to sine x plus 2, right, which is shifted 2 units up on the graph. So remember, our original function is here, so that's a 0. There goes our sine. But when we add 2 to it, we have to shift our graph up 2 units. So now we start at 2, right? On the y-axis. We're starting at 2, and we're going to complete our journey, right? Just shift it up. Same graph, just shift it up. By the way, homework for this has been posted. You probably need this video to complete the homework, I understand. No pressure. All right. So variations of sine and cosine functions. Given an equation of the form f of x is equal to a sine bx minus c plus d, or f of x is equal to a cosine bx minus c plus d, c over b is the phase shift and d is the vertical shift. All right. So now we're going to get into phase shift. Let's look at an example. So identifying the phase shift of a function, right? So we want to determine the direction and magnitude of the phase shift for f of x is equal to sine of x plus pi over 6 minus 2, right? So what am I going to do here? First thing you want to do, let's identify what is C and what is B. Very simple, right? So looking at this, right, I notice my B here is 1 because I don't see a number in front of the x here, so that's going to be 1. So my B is 1. And then I notice that my C term here, right, is what? I have negative pi over 6, right? Negative pi over 6. That's my C term right here. Right? How did I know it was negative? Remember that our original functions always have our C's as negative, right? So the only way that this could be positive is if it's like a minus minus situation, which is what we have over here, right? So C is actually negative pi over 6. Very simple. So what is my formula for phase shift, right? Because that's what I want to know. Determine the direction and the magnitude of the phase shift. So right now, I'm determining the magnitude of the phase shift, right? So the magnitude of phase shift, right? This is the C over B, right? So this is what? Negative pi over 6 over, just to be fair, 1 over 1, right? When you divide this out, you're going to get what? Negative pi over 6. Because you know anything divided by 1 is 1, right? So that's the magnitude of the phase shift, right? Next, we want to determine the direction of the phase shift, right? So, because this is positive, right? Our phase shift is what? Positive, right? We're going to be moving to where? The left, right? Because our phase shift is I'm sorry, I misspoke. Because our phase shift, yeah, I'm just checking. Because our phase shift is negative, sorry about that, we're going to be moving to the left, all right? That's it. And how much to the left are we going to move? Pi over 6 units, right? We're going to move pi over 6 units to the left. There we go, moving to the left. All right, all right, all right. I give you guys a problem to try right now. It says to determine the direction and magnitude of the phase shift where f of x is equal to 3 cosine x minus pi over 2. You can pause the video right now, try it out on a piece of paper, and then come back and click play to see the result of how to do it. All right. I'm gonna give you guys a second to pause. All right, let's take a look at this. All right. So first things first, I want my phase shift, right? Or my magnitude of phase shift, right? So that's going to be what? That's going to be the C over B. That's simple, right? In this case, right, what is C? So my C here is what? Negative. Well, actually, no, it's actually positive. Pi over 2. What's my B? B here is simply just 1. So I have what? I have pi over 2 over 1, which is basically just what? Pi over 2. Oh, let me write that a little way. Pi over 2, right? There we go. So that's my magnitude of the phase shift. Now, let me take a look at this, right? My C is positive, right? So my magnitude is pi over 2. So I'm going to be moving to the what? To the right, right? So, to the right. There we go. Another example. So in this example, excuse me one second. In this example, right, we want to determine the direction and magnitude of the vertical shift for f of x is equal to cosine x minus 3. So I know that my d here is equal to negative 3, right? So what does that mean? That means that I'm going to be shifted down 3 units. So shifted down 3 units. That's it. I'm gonna give you guys one to try on your own. So in this example, you have to determine the direction and magnitude of the vertical shift of f of x is equal to 3 sine of x plus 2. All right, so I'll give you guys a minute to pause. You can pause this video and then try it out on your own. Right, write out the steps, and then you can come back and click play to verify that what you did was correct. All right, so I'm going to give you guys a second to pause the video. So let's get that answer up. So I want to determine the direction and magnitude of the vertical shift of f of x is equal to 3 sine of x plus 2, right? So I'm just concentrating on the vertical shift, right? So that vertical shift is going to be my what? My d, all right? That's my d. I am going to be stretched by 3 as well, right? That's gonna happen as well on top of that. So more specifically, let's talk about what's gonna really happen here. The original sine function, I go up to 1. Instead, my sine function now is gonna go up to 3. My midline is actually gonna jump from 0 to 2, right? So let me just illustrate what I'm talking about real quick. So sine looks like this, right? That's sine. That's y equals sine of x, right? Boom, right? My midline is at x equals 0, right? The x-axis, right? So what I'm saying is, right, instead of me normally going to 1, right? Because remember, I used to go to 1 here and then I go to like -1 down here, right? Instead of that happening, because my amplitude is 3, I'm telling you that I'm actually gonna go to 3 and -3. There it is. 3 and -3. But now when I apply the vertical shift to it, I'm being shifted up. My midline is being shifted up from x equals 0, right? To what? X equals 2, right? So I got shifted up 2. So that means that my max point here when is not at 3 no more. It's actually at 3 plus 2 equal to 5, right? And then my minimum point right here is not at -3 anymore. It's actually at -3 plus 2, which is equal to -1, right? So which direction did I get shifted? I got shifted up, right? So shifted up by 2 units, right? And because I've been stretched, you see how the points have changed, right? So my max unit now is actually 5, and my lower one is going to be -1 instead of the -3, right? Very interesting. So given a sinusoidal function of the form, in the form f of x is equal to a sine bx minus c plus d, we want to identify the midline, the amplitude, the period, and the phase shift, right? All things that we're going to be asking you to do. So first off, we want to determine the amplitude. The amplitude is very simply just the absolute value of a. Two, we want to determine the period, right? How long is this function going to go on for? Amplitude is how high the function will be. Period is how long the function will go on for. So period is equal to 2 pi over the absolute value of b, right? Next, we want to determine our phase shift, right? So when we plug in our traditional values for x, right, where are we shifting them, left or right? The phase shift is determined by c over b, right? And then last but not least, we want to determine our midline, right? Is our midline going to be at 0, or are we going to get shifted up or down depending on if it's being added to our original function or not? Mhm. So now what we want to do is we want to do identifying the variations of the sinusoidal function from an equation. Okay. So we want to determine everything, the midline, the amplitude, the period, the phase shift of the function y is equal to 3 sine 2x plus 1, right? So let's start it off, right? I'm just going to go in order. So I have my midline, right? Normally, you remember that the midline is at x is equal to 0. In this case, my d is 1, right? So d is 1. So I'm going to be shifted up 1 unit, right? So 1 unit, right? Now, right, I want to talk about my amplitude, right? And remember, our amplitude is the absolute value of a, right? So what is that going to be, right? My amplitude is 3, so absolute value of, excuse me, my A is 3, so absolute value of 3 is equal to 3. So my amplitude is 3, right? So what does that mean? That means that my graph is going to be stretched to 3 and -3, right? Graph is stretched from 3 to -3. -3 to 3. Mhm. Next, period. There we go. So my period, right? How long is this function going to go on for? Is 2 pi over the absolute value of b. Let's take a look, right? So I have 2 pi over my b term, right? So b is what in this case is 2, or the absolute value of 2. Let me say it like that. And then that becomes pi over 2, right? And then, so what is this telling me, right? This is, I'm sorry, I should have done this. Boom, boom, and then it's just pi. Sorry about that. I made a mistake. So I have 2 pi over 2, which becomes just pi, right? So what is this telling me? It's telling me that this particular function is going to complete its first merry-go-round, its first period in pi units, right? Or pi spaces away from the what you call it, unit circle, no? Phase shift. Let's talk about phase shift, right? So phase shift. So, hold on one second.
Yes, I'm just checking all of the boards to make sure the erasers, markers are.
Appreciate that. Appreciate that.
No problem.
No markers in here, but.
No,
Well,
well, you know, there's a reason why there are no markers here is because they take them.
oh no.
Yeah, things go missing. If they, yeah, we provide them at the test because you can bring them back.
Got you. Got you. I don't even use them. I use my computer.
Smart. So how long have you been?
Good. Can't
Good.
complain. Yeah.
Yeah,
Good day.
yeah, I know, especially when the pets are away.
Yes.
Yes.
Yeah. Next week will be better.
Well, I was out for 2 weeks, today's my first day back. Thank you. My memory is just like, I miss it. And I'm like, okay, so I'm just coming in tomorrow and I'm out for another 2 weeks.
Nice.
You know what? This year I'm like,
Yeah. Take your rest.
you know what? For all the years I've been here,
Yeah.
it's time to let it go.
Got you.
Just let it be. Stop stressing so much.
Definitely.
Too many Indians. I mean, too many chiefs, not Indians.
Renee. Do
Yeah, no, and this vacation time has made me
think
rethink.
about stuff. I got you.
Yeah, made me rethink and say to myself, I should spend too much of my time here.
Yeah.
It's time for me to let it go.
What you too. What you right there.
All right, good to see
Catch
you.
up. You too. I'll see you in a little bit. All right. Sorry for that commercial break. All right. Oh, Lord. So back to what we are saying. Phase shift is C over B, right? And I forgot my function, so let me scroll back up. Okay. So my A, B, C. My C here is 0, right? I don't know why this came out the way it came out. Okay, it's working. Let me try this again. So phase shift is C over B. Here we go, right? And looking back on my function, right? I see here that my C is 0, and I know that my B is 2, right? Let me just go back up to show you guys. So we have 3 sine 2x plus 1. Nothing's being added to the 2x, therefore my C is 0. All right, which means that my phase shift is 0. So what is that telling me? That's telling me that my graph will not be shifted at all, right? I'm not going to the left or the right. I'm going to remain right where it originally started. You know, this is sine, right? If I'm not mistaken. This is sine, so we're gonna start at the origin, right? We're gonna start at the origin. Okay, good stuff.
Mhm.
Oh, by the way, kind of overlooked this, right? Our midline is 1, right? So when you heard me say we're going to start at the origin, right? I'm really saying we're going to start at y equals 1, right? So our first point would be 0, comma 1, right? Not 0, 0, the origin, right? Because we got shifted up 1 unit. Okay. 1 second, please. Okay. So I just want to take a look at this real quick just to make it pop, right? So inspecting the graph, we can determine, sorry about that. Inspecting the graph, we can determine that the period is pi, the midline is y equals 1, and the amplitude is 3, all right? So our midline right here, as you can see, is y equals 1. We're going to start at the midline, go up to our max, right? Which our amplitude was 3. So 3 more units up is at 4. Then we're going to go down, right? Back to our midline, right? Which is y equals 1. Then from our midline, we're going to go down to our max, which in this case will be -2, and then right back up to our midline. All right. And of course, our period is pi, so we're only going out pi units, right? We've been compressed, right? Horizontally, right? So here we want to determine the midline, the amplitude, the period, and the phase shift of the function. Y equals 1/2 cosine x over 3 minus pi over 3. All right, so I'm going to give you guys a second to pause the video. You could pause and try this on your own. And then after that, come back and click play to see the answer. Let me give you guys a second. Awesome. Now let's take a look at this, right? So my midline is equal to our D term, right? But I notice in this question, I have no D term, right? So that means that D is equal to 0. Therefore, this particular graph will not be shifted up or down, right? We're going to be right there at the line x equals 0, right? So, right, for clarification. Next thing, we want to talk about the amplitude. I'm just going to call that amp, right? That's going to be equal to what, right? So our amplitude, right, it will be equal to the absolute value of A. Hold on a second. Bear with me 1 second, please. Right. So my amplitude, once again, is the absolute value. Sorry about that. Is the absolute value of A, right? Which we know in this case, right, is actually going to be the absolute value of 1/2, right? So my amplitude is equal to 1/2, right? What does that tell me, right? That tells me that my graph is going to be compressed, right? We're going to be compressed to half vertically by half. Okay, there we go. All right. That's my amplitude. What's next? Period. So my period will be equal to 2 pi let's see. Sorry about that, you guys. Just put that in. Hopefully that fixes everything. Let's try that now. Awesome. I didn't realize that my battery was going a little bit low. That's why everything was moving a little bit slow. Okay. So anyway, my period is equal to what? 2 pi over the absolute value of b, right? So this is going to become what? 2 pi over the absolute value of b. What's my b term here, right? Right here. That's going to be my 1/3, right? And then you already know, right? This is going to become absolute value of 1/3 is just 1/3. So 2 pi over 1/3. Let me scroll down just a little bit. So this is going to become 2 pi over 1, keep change flip, times 3 over 1, call that 6 pi, right? So my graph will complete a full rotation, a full period at 6 pi. Right? So we're gonna be going out long with this one, right? Phase shift. So my phase shift is equal to what? Phase shift, yep, good. Got it. Is equal to C over B, right? In this case, let's look at what my C term is, right? Is pi over 3, right? My C term is pi over 3 over what is my B term? 1/3, right? You already know, keep change flip. So pi over 3 times 3 over 1. These will cancel. So what do I get? Pi. So I have a phase shift of pi. So what does that mean? That means I'm going to be shifting my graph, right, over to the right by an amount of pi, right? So shifted by pi units. Okay, good stuff, good stuff, good stuff. All right. Anything else? No, that's it. Let's talk about graphing variations of y equals sine x and y equals cosine x. So throughout this section, we have learned about types of variations of sine and cosine functions and used that information to write equations from graphs. Now we can use the same information to create graphs from equations instead of focusing on the general form equation. So y equals a sine of bx minus c plus d and y equals a cosine of bx minus c plus d. So we will let C equals 0 and D equals 0 and work with the simplified form of the equations in the following examples. All right. Before we do that, let me give you guys a little how-to. So given the function y equals a sine bx, we want to sketch its graph, right? So the first thing we want to do is identify the amplitude, right, which is the absolute value of a. Second thing we want to do is identify the period, which will be 2 pi over the absolute value of b. Third, we want to state at the origin, right, with the function increasing to the right if a is positive or decreasing if a is negative, right? Um, at x equals pi over 2b, there will be a local maximum, right? If a is greater than 0, or a minimum if a is less than 0, right? With y equals a. The curve returns to the x-axis at x equals pi over the absolute value of b. And there is a local minimum for a greater than 0, right? Maximum for a less than 0 at x equals 3 pi over 2b, right? With y equals negative a. So the curve returns again to the x-axis at x is equal to 2 pi over the absolute value of b. Okay. And again, this is for graphing the function a sine of bx. Okay. So now we're graphing a function and identifying the amplitude and period. So here we want to sketch the graph of f of x is equal to negative 2 sine pi over 2x, right? If it's okay, I just want to rewrite this, right? I want to rewrite this as second. I'm going to rewrite this as f of x is equal to negative 2 sine pi over 2x. I don't know. I feel like it just pops a little bit more when I do that, right? So let's go through the motions, right? What do I have? I have an amplitude, right? Which is equal to absolute value of negative 2, which is 2. So what do I know? I know that my graph is going to go from the sine, right? It's going to go from 0 to negative 2 or from 0 to 2, right? That's going to be my max, all right? What else do I have? Let's look at our period, right? Let's look at how long we have to go out. So that's going to be what? 2 pi over the absolute value of b, right? So then this is going to become 2 pi over our b term. In this case, our b term is what? Pi over 2, the absolute value of it, which is just pi over 2. And then you already know, keep change flips. I'm going to keep 2 pi over 1 times 2 over pi. Kill these. It's just going to be 4. So my period is 4. All right. And then let's look at our phase shift. Phase shift over here, we know is C over B. In this case, my C is 0, my B is pi over 2. Therefore, phase shift is 0. That means I won't be shifting my graph to the left or to the right. It's just going to be at its original state, right? Let's look at, what am I forgetting? Midline. In this case, I have no number being added to this, right? So my D is equal to 0. So I will be at x equals 0. Just want to scroll up, see what am I missing? What am I missing? What am I missing? Got the amplitude, period. Da, da, da. All right. So I guess we could start this off, right? So I'm gonna be drawing a sine function. And I know that sine starts at 0, and my in the original question, my a is -2. So what do I know? I know that I'm gonna start over here at 0, and I'm gonna go down to -2, right? This is -2 right here. And then I'm gonna go back up to the x-axis, then go over here, and then so on and so forth, right? That's that. But now I can't just draw it like, oh, this is 2, by the way. I can't just draw it like this. I have to put in some x values with this, right? So when x is 0, right, we have -2, right? Sine of 0. So when x is 0, let me just plug it in. Probably be easier if I just did a table of values. So I'm saying when x is 0, right? My equation became what? Let me take a look. Anything times 0 is 0. So -2 sine of 0. Sine of 0, we know is, see, when x is 0. Sine is 1. So 1, -2 times 1 is just -2. All right? Trying to think, does that sound right? No, that is right. When x is 0, yeah. But when x is 1, let's take a look at what that would look like. When x is 1, right? That would be pi over 2. Sine of pi over 2, we know is 1. So that's -2. Wait, maybe I have this wrong. This is 0. Sine of 0 is 0. There we go. Now it's making more sense. All right. Yeah, that's making more sense. And then so on and so forth, right? If I keep going, let me see, shifted 0, period is 4, amplitude is that. So for the most part, everything should stay the same, right? So if I plugged in, what's another one? Let me see what happens at pi over 2. Let's talk about that. Pi over 2, right? Pi over 2 is 90 degrees, right? So then if I plug that in, that's going to become like pi squared over 4, right? Hmm, 1 second. Do, 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 do. Just trying to verify. Yep, that's right. I was to plug in 3, right? Then this would become 3 pi over 2, and then 3 pi over 2 sine is negative 1. So negative 1 times negative 2. Shoot, that's positive 2. There we go. All right. So this would be the point 1 comma negative 2, right? And this would be the point 3 comma 2. All right. And then, of course, if I plugged in 4, sine of 2 pi is just 0. So this right here, this is 4. And that point would be 4 comma 0. All right. 4, and then sine of 2 pi is 0. And anything times 0, you already know is 0. So boom. All right, that's it. That's our curve right there. So basically, when you're graphing these, you want to name out all of these things: amplitude, period, phase shift, midline, all of that. And then you can just plot some points, plot the graph, and that's it. Okay. Sometimes it can be a little tricky, I understand. Also, not depending on the question, sometimes they may ask you to do more than one cycle. If that's the case, then you just continue doing the same thing, plugging in numbers and plotting your points, and that's it. All right. So that being said, let me give you guys a little how-to. All right, so given a sinusoidal function with a phase shift and a vertical shift, let's sketch its graph. So what you have to do first is express the function in the general form y equals a sine bx minus c plus d, or y equals a cosine bx minus c plus d. Identify the amplitude, which is a. Identify the period, which is equal to 2 pi over the absolute value of b. And then 4, you want to identify the phase shift, which is c over b. Draw the graph. F of x is equal to a sine bx, shifted to the right or left by c over b, and up or down by d. Okay, so that's how we do those graphs. Look at another example. So here they just ask us to sketch the graph of f of x is equal to 3 sine pi over 4x minus pi over 4. Let's start it off, right? So we want to do our amplitude first. So absolute value of amplitude is going to be absolute value of 3 is equal to 3, all right? So we know that our graph is going to 3 with each interval, all right? So next, let's talk about our phase shift. Which is equal to C over B. In this case, my C is what? It's pi over 4 divided by my B, which is what? Pi over 4. Anything divided by itself, you already know is 1. All right, so there we go. Next, we want to talk about our period. All right, so the period is going to be equal to 2 pi over the absolute value of B. All right, then we're just going to plug in some numbers. This is going to become 2 pi over pi over 4, right? Absolute value, of course, which becomes pi over 4. So now what we want to do, keep change flip. This is 2 pi over 1 times 4 over pi. Pi's cancel. This is what, 8. So a full period for me is going to go all the way out till 8. And my phase shift is 1. All right. Midline. So my midline here, my D is equal to 0. So I'll be at x equals 0. So making sure I didn't forget anything. Period, amplitude, phase shift, good to go. All right. So phase shift this is positive, so we're gonna move over to the righty right. Right? What am I graphing? Sine, right? All right. So let's plug in some numbers here. Let's plug in 4, for example. All right. If I plug in 4 up top, that becomes just pi, right? So pi minus pi over 4. Um, that becomes 3 pi over 4, right? And then sine of 3 pi over 4. Mm, yeah, that's not a good number. It's going to be a decimal. Definitely plug in 8. That's going to become 2 pi or 8 pi, which is 7 pi over 4. Yeah, this one's not pretty. This one's not pretty. One option you guys have is you can use your table of values, but your table of values will not give you nice answers. So the best thing to do would be to plug in ideal x values, 1, 2, 3, 4, whatever, or pi over whatever, and then see what the y value would be for that, right? But just drawing this in general, right? My phase shift is 1. So normally speaking, you remember for sine, I start at the origin, right? I'm not going to start at the origin, right? Instead, I'm going to start at 1. And then, boom, that's one cycle for me, right? I know at 4, this has to occur where that's 0. And at 8, that will also happen at 0. Right? But in between 1 and 4, let's say I plug in 2, this will become just regular pi over 4. And sine of pi over 4, if I'm not mistaken, is 1. That's like sine of 45 degrees, right? So I got that by plugging in 2. So this right here is 2, which means that this must be 6. Because this is the point 2 comma 3. Let me check that. Let me verify. Amplitude is 3. Yep. And then this would be the point 6 comma -3. There we go. And that's it. Just plug in your numbers. You figure out what the y values will be, right? It's good to figure out the zeros. That helps. Then you're good to go. By the way, how did I know that 8 would be 0? Right? Because the period, remember, it's going to always end on the axis, right? So I knew that that would be a 0. Didn't know how, but I knew that it would be. Okay. Feel like we're good with this. The idea was there. Let's move on. So we know the tangent function can be used to find distances such as the height of a building, a mountain, or a flagpole. But what if we want to measure repeated occurrences of distances? Imagine, for example, a fire truck parked next to a warehouse. The rotating light from the truck would travel across the wall of the warehouse in regular intervals. If the input is time, the output would be the distance the beam of light travels. The beam of light would repeat the distance at regular intervals. The tangent function can be used to approximate the distance. Asymptotes, right, would be needed to illustrate the repeated cycles when the beam runs parallel to the wall because seemingly the beam of light could appear to extend forever. So the graph of the tangent function would clearly illustrate the repeated intervals. So in this section, we will explore the graphs of tangent and other trigonometric functions. Okay, just a quick recap. So we're going to be analyzing the graph of y equals tan x. So we will begin with the graph of the tangent function, plotting points as we did for the sine and cosine functions. Recall that tan of x is equal to sine of x divided by cosine of x. The period of the tangent function is pi because the graph repeats itself on intervals of k pi, where k is a constant. If we graph the tangent function on negative pi over 2 to pi over 2, we can see the behavior of the graph of one complete cycle, right? If we look at any larger interval, we will see that the characteristics of the graph repeat. So we can determine whether the tangent is an odd or even function by using the definition of tangent, right? So tan of negative x is equal to sine of negative x divided by cosine negative x. Cosine is an even function, sine is an odd function, therefore tan is a odd function. Very good, very good, very good. So therefore tangent is an odd function. We can further analyze the graphical behavior of the tangent function by looking at values for some of the special angles as listed here, negative pi over 2, negative pi over 3, etc. Right? So where tan will be undefined, negative square root of 3, negative 1, etc. Right? So these points will help us draw our graph, but we need to determine how the graph behaves where it is undefined. If we look more closely at values when pi over 3 is less than x, which is less than pi over 2, we can use a table to look for a trend because pi over 3, which is similar to 1.05, and pi over 2, which is similar to 1.57, right? We will evaluate x, right, at random measures from 1.05 to 1.57 in the table. So as x approaches pi over 2, the outputs of the function get larger and larger because y equals tan of x, right, is an odd function, right? We see the corresponding table, right, of negative values, right? So in table 3, right, x is negative 1.3, but our tan is negative 3.6, etc. So we can see that as x approaches negative pi over 2, the outputs get smaller and smaller. Remember that there are some values of x for which the cosine of x is equal to 0. So for example, cosine of pi over 2 is equal to 0, and cosine of 3 pi over 2 is equal to 0. Right? So at these values, tangent function is undefined, right? So the graph of y equals tan of x has discontinuities, right? At x equals pi over 2 and 3 pi over 2, right? At these values, right, the graph of the tangent has vertical asymptotes, right? So, okay. This figure represents the graph of y equals tan x. The tangent is positive for 0 to pi over 2 and from pi to 3 pi over 2, corresponding to the quadrant 1 and 2 in the unit circle. So there you go. We have our vertical asymptote at pi over 2 and at negative pi over 2. And that's it. Okay. Now let's talk about graphing variations of y equals tan x. As with the sine and cosine functions, the tangent function can be described by a general equation y equals a tan bx. We can identify horizontal and vertical stretches and compressions by using the values of a and b. The horizontal stretch can typically be determined from the period of the graph. With tangent graphs, it is often necessary to determine a vertical stretch using a point on the graph, right? Because there's no maximum or minimum values of a tangent function, the term amplitude cannot be interpreted as it is for the sine and the cosine functions. Instead, we will use the phrase stretching or slash compressing factor when referring to the constant a. So let's take a look at our toolbox real quick. Let's take a look at our toolbox. All right. So these are features, right, of the graph of y equals a tan bx. So the stretching factor is the absolute value of a. The period is p is equal to pi over the absolute value of b for tan. You notice the difference? The domain is all real numbers x, where x does not equal pi over 2 times the absolute value of b plus pi over the absolute value of bk, such that k is an integer, right? The range is, of course, negative infinity to infinity. The asymptotes, this is important, the asymptotes occur at x is equal to pi over 2 times absolute value of b plus pi over the absolute value of bk, where k is an integer. So y equals a tan bx is an odd function, right? Remember that from before. All right. So graphing one period of a stretched or compressed tangent function, we can use what we know about the properties of the tangent function to quickly sketch the graph of any stretched and or compressed tangent function of the term f of x is equal to a tan bx. We focus on a single period of the function, including the origin, because the periodic property enables us to extend the graph to the rest of the function's domain if you wish. Our limited domain is then the interval negative p over 2 to p over 2. And the graph has a vertical asymptote at plus or minus p over 2, where p, right, is equal to pi over b, right? Our period, right, on negative pi over 2 to pi over 2. The graph will come up from the left asymptote at x equals negative pi over 2, cross through the origin, and continue to increase as it approaches the right asymptote of x equals pi over 2. So to make the function approach the asymptote at the correct rate, we also need to set the vertical scale by actually evaluating the function for at least one point on the graph will pass through. So for example, we can use f of p over 4 is equal to a times tan of b times the period over 4, which is equal to a tan b of pi over 4b, which is equal to a. So because the tan of pi over 4 is equal to 1, let's take a look. Let's look at a little how-to real quick. A little sauce right here. So given the function f of x is equal to a tan of bx, we want to graph one period. So here's how we do it. Identify the stretching factor, which is the absolute value of a. Identify b and determine the period, right? So period is equal to pi over the absolute value of b. Draw the vertical asymptote at x is equal to negative period over 2. And the, what you call it, the other asymptote at x is equal to the period divided by 2. For a times b greater than 0, right? The graph approaches the left asymptote at negative output and the right asymptote at a positive output. And the reverse is true for a times b less than 0, right? Then it's going to be the reverse, right? So when we approach the left, it'll be going up. When we approach the right, it'll be going down. Plot reference points at the period divided by 4 times the amplitude, or is the amplitude, and 0, 0, of course, because that we're always going to cross the origin. And of course, negative p over 4 and negative the amplitude, right? To draw the graph through the points. Okay. Let's try this out. We'll keep this one simple, right? So stretching a compressed tangent function. So we have y is equal to 0.5 tan of pi over 2x. So I know that my a in this case is going to be equal to 0.5. And I know that my b in this case is equal to what? Pi over 2, right? So my stretching factor, absolute value of a, is going to be absolute value of 0.5, which is equal to 0.5, right? My period, right? P, I think where I want to do that. I'll do it down here. My period P is going to be equal to pi over the absolute value of B, right? Which is going to give me what? Pi over absolute value of pi over 2, which is again pi over 2. And you already know keep change flip. So this is pi over 1 times 2 over pi. Pi is canceled. This is just going to be 2, right? And then we're going to have a vertical asymptote. We're going to have a vertical asymptote at x equals the period divided by 2. Let me verify that, please. Okay. At the period divided by 2 and at negative the period divided by 2. So our period was what? 2 over 2, call that 1. And this period would be negative 2 over 2, call that negative 1. There we go, right? And then we have to do a times b. So let's do that real quick. I'm just going to change this to a fraction, make it a little bit easier. This is 5 over 10, which becomes 1 over 2. Okay, so if I do a times b, this is going to be what? 1/2 times pi over 2, which becomes what? Pi over 4, right? Now, since pi over 4 is greater than 0, right? As the graph approaches the left asymptote, we're going to be negative, right? So let's look at this now. Let's look at this now. Oh, of course, we have the origin. Let me not forget that, right? We have the origin, right? I'm going to cross the origin at 0, 0. So here's how it's going to look. Let's call this -1. Let's call this 1. Put some dash lines down here. This is representing the asymptote, right? So of course, this is x equals 1. This is x equals -1, right? Origin right here. We're going to cross that point. It's the point 0, 0. And I told you as we go to the left, negative infinity, come up, and we're going to go right up here to the right. That's your tangent graph. All right. This is y equals 0.5 tan pi over 2x. That's it. Mm. Missing something. Last one. Okay. Reference points. Reference points, right? I'll just box some of these in just so I'm not confused. Just want to box some of those in. So for our reference points, right, we need the period over 4 and the amplitude. Excuse me. So our period was 2 over 4, and the amplitude was what? 1 over 2. That's 1 point, right? Simplify that down, it's actually 1/2, comma 1/2. Another point that we're going to have is negative the period over 4 and negative the amplitude, which is negative 1/2. So this is just negative 1/2, comma, negative 1/2, right? And of course, the origin. So we can actually plot those points, right? So in the middle, this point right here, this is the point half, comma, half. And also right here, this is the point negative half, comma, negative half. All right? And that's it. That's my tan graph. Just want to talk about this so we have some understanding. So graphing one period of a shifted tangent function. Now that we can graph a tangent function that is stretched or compressed, we will add a vertical and or horizontal phase shift. In this case, we add c and d to the general form of the tangent function. So f of x is equal to a tan bx minus c plus d. So the graph of a transformed tangent function is different from the basic tangent function tan of x in several ways. Okay. Let's talk about the features difference. Okay. So features of the graph of y equals a tan bx minus c equal plus d, excuse me, right? So a stretching factor is the absolute value of a. The period is actually pi over the absolute value of b. The domain is x not equal to c over b plus pi over 2 absolute value of b k, where k is an integer. The range is, of course, negative infinity to infinity. The vertical asymptote is going to be at c over b plus pi over 2 absolute value of bk, where k is an odd integer, and there is no amplitude, right? There's no amplitude here. So given the function y equals a tan bx minus c plus d, say we want to sketch the graph of one period, right? So to do that, first express the function given in the form y equals a tan bx minus c plus d. Identify the stretching or compressing factor as the absolute value of a. Step 3, identify b and determine the period, which is again pi over the absolute value of b. Step 4, identify C, right? And determine the phase shift, which is C over B, right? Step 5, draw the graph of y equals a tan bx, shift it to the right by C over B and up by D, right? And step 6, shift the vertical asymptote, right? Which is at x equals C over B plus pi over 2 absolute value b, where k is an odd integer. And then step 7, plot any reference points and draw the graph through these points. All right, let's look at how to do an example real quick. So graphing one period of a shifted tangent function. So we want to graph one period of the function y is equal to negative 2 tan pi x plus pi minus 1. All right. So we're gonna do this step by step, right? I'm gonna show you guys this more formally written because my handwriting can get a little messy at times. And I feel like the last one was kind of messy. So step 1, right? The function is already written in the form of y is equal to a tan bx minus c plus d. Step 2, we know that our a term here, right? Our a term is negative 2, right? So the stretching factor is 2. We know that our b term is pi, right? So the period is pi over the absolute value of b, or pi over pi, which equals 1. That's our period, right? Our c term, we know, is going to be negative pi. So the phase shift is negative pi over pi, or negative 1. And then for 5 through 7, we have an asymptote at the period, right? The period divided by 2, right? No, hold on a second. How did we get that again? One second. The period divided by 4 times the asymptote, right? That's our reference point, right? Let's come back here. So our period, which is 1, right? Which should be divided by 4, right? But in this case, that didn't happen. So we have x equals negative 3 over 2 and x equals negative half, right? Boom. Here we go with our reference points, right? And here's our graph. Boom. All right. So just want to make a special note. This is a decreasing function because our a is negative, right? So notice how we swapped as we're going to the left asymptote, we're going to infinity. The right asymptote, we're going to negative infinity. Let's look at what else we're getting into. So for any right triangle, given one other angle and the length of one side, we can figure out what the other angles and sides are. But what if we are given only two sides of a right triangle? We need a procedure that leads us from a ratio of sides to an angle. This is where the notion of an inverse to a trigonometric function comes into play, right? So in this section, we will explore the inverse trigonometric function. So, well, essentially what I'm saying is, right, I have some kind of triangle, right? And I know two of the legs of the triangle, right? So if have this right triangle, I'm telling you that I know what leg A and what leg B is, right? But what I really want to know is what is angle A, right? Or let's call it angle alpha, right? For A. What is that? I don't know what it is, right? And of course, there's a leg C. That's capital C, B, right? What is angle alpha, right? I know what this is, and I know what this is. Trigonometric functions are going to give that to us. All right. So let's talk about that for a little bit. All right. So understanding and using the inverse sine, cosine, and tangent functions. So in order to use inverse trigonometric functions, we need to understand that an inverse trigonometric function undoes what the original trigonometric function does, as in the case with any other function and its inverse. So in other words, the domain of the inverse function is the range of the original function and vice versa as summarized, right? So for a trigonometric function, domain is the measure of the angle, and the range, right, is the ratio, right? But for the inverse trigonometric function, it's flipped. The domain is the ratio, and the range is the measure of the angle, right? All right, let's look at an example real quick because that's a lot, right? So for example, let's say that we have f of x is equal to sine x. Then we would write f inverse of x is equal to sine inverse of x. Be aware that sine inverse of x does not mean 1 over sine x, right? So the following examples illustrates the inverse trigonometric function. So if I have sine of pi over 6 is equal to 1/2, right? Then pi over 6 will be equal to the sine inverse of half, right? I switch to x and the y's, inverses, very simple, right? So the cosine of pi is equal to -1, then pi will be equal to the cosine inverse of -1. Right? Keep it simple, right? And since tan of pi over 4 is equal to 1, then pi over 4 will be equal to the tan inverse of 1. So in previous sections, we evaluated trigonometric functions at various angles, but at times we need to know what angle would yield a specific sine, cosine, or tangent value. For this, we need inverse functions. Recall that for a one-to-one function, f of a is equal to b, right? Then an inverse function would satisfy the f inverse of b equal to a. All right. So bear in mind that the sine, cosine, and tangent functions are not one-to-one functions. The graph of each function would fail the horizontal line test. In fact, no periodic function can be one-to-one because each output in its range corresponds to at least one output in every period, right? And there are an infinite number of periods as with other functions that are not one-to-one. So we will need to restrict the domain of each function to yield a new function that is one-to-one. So we choose a domain for each function that includes the number 0, right? As you see in figure 2, right? It shows the graph of the sine function limited to negative pi over 2 to pi over 2. And the graph of the cosine function, right? Notice it's starting at 1, which is limited to 0 to pi, right? This is the only way we can do this because they're not one-to-one. So figure A, sine function on a restricted domain from negative pi over 2 to pi, right? And we know this because we're starting at 0. And then cosine function on the restricted domain from 0 to pi, we know this is because it's starting at 1, right? So this graph shows the graph of the tangent function limited to negative pi over 2 to pi over 2. All right, very good. So these conventional choices for the restricted domain are somewhat arbitrary, but they have important, helpful characteristics. Each domain includes the origin and some positive values, and most importantly, each result is a one-to-one function that is inevitable, right? Invertible, excuse me. Um, the conventional choice for the restricted domain of the tangent function also has the useful property that it extends from one vertical asymptote to the next instead of being divided into two parts by an asymptote. So on these restricted domains, we could define the inverse trigonometric function. So the inverse sine function, y equals the sine inverse of x, means that x is equal to sine of y, right? So the inverse sine function is sometimes called the arcsine function and is noted as arcsine of x. So y equals sine inverse of x has domain -1 to 1 and range -π/2 to π/2. The inverse cosine function, y equals cosine inverse of x, means that x is equal to cosine of y. The inverse cosine function is sometimes called the arc cosine function and is noted as arc cosine of x. So y equals the inverse of x has domain -1 and range 0 to pi. There we go. Let's take a look at that. So the graphs of the inverse functions are shown, right? Notice that the output of each of these inverse functions is a number, an angle in radian measure. So we see that sine inverse of x has domain -1 to 1 and range -π/2 to π/2. Cosine inverse, right, of x has domain -1 to 1 and range 0 to pi, right? Tan has all real numbers, etc. So to find the domain and range of inverse trigonometric functions, you want to switch the domain and range of the original function. Each graph of the inverse trigonometric function is a reflection of the graph of the original function about the line y equals x. Okay. So here you can see we have the sine of x right here, starts at 0, bop, bop, right? But the inverse, right, inverse function, right, we're flipping over the line y equals x, right? So again, we started the origin, but we go outward, right? Let's make it fair. Let's look at cosine. So cosine inverse of x, so our turquoise line, our dark blue, is our original cosine function. Notice that we started at 1. Boom, boom. All right. We're reflecting over the line y equals x. So that's why we're up a little bit more. So the cosine function and the inverse cosine or the arc cosine function, right? So we can also call this arc cosine of x. All right. So the relations for inverse sine, cosine, and tan functions, the angles in the interval from -π/2 to π/2. If sine of y is equal to x, then the sine inverse of x is equal to y. The angles are in the interval 0 to pi, right? If cosine y of x is good, right? Then the cosine inverse of x will be equal to y. So say we want to write relations for an inverse function. So given that sine of 5 pi over 12 is equal to 0.96593, you want to write a relation involving the inverse sine, right? So very simply, this is how we do this, right? You're gonna swap the x and the y. That's it. You're just swapping them. So what am I telling you? I'm telling you that sine of 0.96593 is equal to 5 pi over 12. And there you go. That's it. We'll just swap the x and the y. Okay. So finding the exact value of expressions involving the inverse sine, cosine, and tangent functions. Now that we can identify inverse functions, we will learn to evaluate them. For most values in their domain, we must evaluate the inverse trigonometric function by using a calculator in interpolating from a table or using some other numerical technique, just as we did with the original trigonometric functions. We can give exact values for the inverse functions when we're using the special angles, specifically pi over 6 or 30 degrees, pi over 4 or 45 degrees, and pi over 3 or 60 degrees, and their reflections into the other quadrants. So given a special input value, evaluate the inverse trigonometric function. So find x for which the original function has an output equal to the given input for the inverse trigonometric function and find x if x is not in the defined range of the inverse, find another angle y that is in the defined range and has the same sine, cosine, or tangent value, depending on which corresponds to the given inverse function. So here we want to evaluate inverse trigonometric functions for a special input value. So we want to know what is the sine inverse of a half, right? So a couple ways we could do this, right? I'm trying to think of the easiest way that we could do it. First off, angle, the leg value that we have here is positive, right? So whenever I'm using the unit circle, right? Where is sine positive? Sine is positive here. Sine is positive here, right? If this angle that I'm looking for, right? This is x right here, right? So the angle x is really what I'm looking for given the leg 1, 2. So this is x and this is x. I want to know what is x, right? So sine is what? Opposite over hypotenuse, right? As soon as I see the 1 and the 2, I know what this is. This is radical 3, right? Because special right triangle. Opposite the 1 is angle 30 degrees. Look at that, I'm already done. This is 60 degrees, this is 90. X is 30 degrees again over here. This is 90, this is 60 degrees. This is 2, this is 1, this is negative radical 3. So I'm done. So I know that the answer for this is 30 degrees or 30 times pi over 180, which is what? Pi over 6. Simple, right? I hope it's not too complicated. All right, and then you just go through doing the rest of them, right? So, oh shoot. Hold on one second. Okay, I'm good. So I'm gonna erase this. Just rewind the video if you want to see this back, because I just want to kind of keep the space the way it is. I will, however, scroll down a little bit. Make it a little bit bigger. Okay, there we go. So I have sine inverse is equal, excuse me, I want to know what the sine inverse of negative square root 2 over 2, right, is equal to x, right? I want to figure out what x is. So let's go back to our quadrants, right? Where is sine negative? Well, we know sine is negative down here, and we know sine is negative down here. I'm telling you, this is the angle x that I'm looking for, right? Now, this says that the sine inverse of negative radical 2 over 2, right? So I could just tell, this is 90 degrees, by the way. This is 90 degrees, right? By the way, right? Radical 2 over 2, the only special right triangle that has that, it has side 1, 1. This is going to be negative 1, of course, radical 2. And then this one would be negative 1, negative 1, radical 2. There we go, right? Very simply, sine is what? Sine is opposite over hypotenuse, right? This special right triangle is a what? 45 degree triangle, right? So what's the answer to x? 45 degrees, or if you want, you can do 45 times pi over 180, whatever makes you happy. Um, Trying to remember what that is. All right, so that's pi over 4. There we go. Cancel. No. Sorry about that. So this is pi over 4. All right. You do the same thing for the cosine. I'm gonna scroll down a little bit. Again, if you want to see this again, just right here. Rewind the video so you can see. I'm gonna erase this. Okay. So I want to know what is a cosine inverse of negative square root 3 over 2. So very simple. I'm going back to my unit circle. Where is cosine negative, right? So cosine is negative here, and cosine is negative here. Very simply, right? This is my x that I'm looking for, right? So cosine is what? It's adjacent over hypotenuse. So this is my adjacent. It's negative square root 3, right? Over the hypotenuse, which is 2. So that means that this must be 1 and negative 1, right? So that being said, right, opposite the 1 we know is what? This is 30 degrees. So that's 60 degrees. And this is 90, right? 30 degrees, 60 degrees, and this is 90. So what's x? X is 30 degrees. Or what did we say this was again? 30 times pi over 180. Believe it's pi over 6. Not too bad, right? And tan of 1, you already know is 45. That's it. You want to see tan is positive down here. and positive up here. This is x, right? I know it's 1 because the only way you can get a 1 out of these triangles is with -1, +1, right? Radical 2, 1, 1, radical 2. So this has to be 45. And that's it. So tan of 1 is equal to 45 degrees. Or if you want, 45 over 180 times pi over 4. And that's it. Give you a little instruction. So given two sides of a right triangle like the one shown below, if one side of the hypotenuse, oh, excuse me, if one given side is the hypotenuse of length h and the side of length a adjacent to the desired angle is given, use the equation theta is equal to cosine inverse of a over h, and that'll give you your angle. If one given side of is the hypotenuse length h and the and the side of length p is opposite the desired angle is given, use the equation theta is equal to sine inverse, which is of p over h. And that's it. All right. Sometimes you might run into having to use a calculator for this. You guys know how to type that in. If you don't, go to tutoring and ask. Otherwise, let's move on. Finding exact values of composite functions with inverse trigonometric functions. So there are times when we need to compose a trigonometric function with an inverse trigonometric function. In these cases, we can usually find exact values for the resulting expressions without resorting to a calculator, even when the input to the composite function is a variable or an expression. We can often find an expression for the output. To help sort out differences, right? Let f of x and g of x be two different trigonometric functions belonging to the set sine of x, cosine of x, tan of x, right? And let the inverse of y and the inverse of the f inverse of y and the g inverse of y be their inverses. So evaluating compositions of the form f of f inverse of y and f inverse of f of x, right? So let's recall, for any trigonometric function, f of f inverse of y is equal to y. For all y in the proper domain for the given function, this follows from the definition of the inverse and from the fact that the range of f was defined to be identical to the domain of f inverse. However, we have to be a little bit more careful with expressions of the form f inverse of f of x. Let's take a look at y. So compositions of a trigonometric function and its inverse. So sine of sine inverse of x is equal to x. That's how we know that two functions are inverses, of course. For -1 to 1, cosine of cosine inverse of x is equal to x. For -1 less than x less than 1, right? Sine inverse of sine x is equal to x only for -pi/2 less than or equal to x less than or equal to pi/2. And cosine inverse, cosine of x is equal to x only for 0 less than or equal to x less than or equal to pi. Okay. Is it a question? So is it correct that the sine inverse of sine of x is equal to x? No. This equation is correct if x belongs to the restricted domain, -pi/2, pi/2, but sine is defined for all real input values, and for x outside the restricted interval, the equation is not correct because its inverse always returns a value in -pi/2 to pi/2. The situation is similar for cosine and tangent in their inverses. For example, sine inverse of sine of 3 pi/4 is equal to pi/4. Okay. Long story short, it sounds like solve the inside before you solve the outside. Okay. So given an expression of the form f inverse of f of theta, where f of theta is equal to sine theta, cosine theta, or tangent theta, you want to evaluate. This is how you do it. Step one, if theta is in the restricted domain of f, then f inverse of f of theta is equal to theta. If not, then find the angle theta, phi, excuse me, within the restricted domain of f, such that f of phi is equal to f of theta. All right. Then f inverse of f of theta is equal to um phi. Okay. But this is not bad. This is kind of similar to what we did before. Let me start it off. So what you want to do, right? You want to do the inside first. So sine inverse of sine of pi/3. Let's do that inside first, right? So what is sine of pi/3, right? Let's recall pi/3 is, let me do this over here, pi/3, all right? So that's going to be 60, I believe. Sorry about that. Okay, so that's 60 degrees, right? So essentially, I'm asking what is sine inverse of sine of 60 degrees, right? Now, special right triangle right here, right? This is, let's call this 60 degrees, call that 30 degrees. Opposite of 30 is 1. Opposite of the 60 is square root 3, and this is 2. So sine of 60 is going to be square root 3 over 2. So this becomes what? I want to know what is a sine inverse of square root 3 over 2. Very simply, right? So let's figure that one out, right? From under quadrants right here, right? Where is sine positive, right? Sine is positive here. Got x right here. Sine is positive here. Got x right here, right? So sine is what? Opposite over hypotenuse, opposite over hypotenuse, right? And then this would be 1 and -1. There we go. So sine of square root 3 over 2, right? That's going to work out to be what? Opposite the 30-degree angle is 60 degrees, right? So this is just simply pi over 3. And you can do the same process for all of them, right? Going through. I mean, I like to switch it to decimal, go straight to the circle, and figure it out. Right? Kind of looking at time, so I want to wrap this up. So evaluating compositions of the form f inverse of g of x. So now that we can compose a trigonometric function with this inverse, we can explore how to evaluate a composition of a trigonometric function and its inverse of other trigonometric functions. So we will begin with compositions of the form f inverse of g of x. For special values of x, we can exactly evaluate the inner function and then the other. So inverse function, the other inverse function. However, we can find a more general approach by considering the relation between the two acute angles of the right triangle where one is theta, right? And making the other pi over 2 minus theta. So consider the sine and cosine of each angle in the right triangle. Here we go. So because cosine of theta, cosine being adjacent over hypotenuse, is b over c, this equals that sine of pi over 2 minus theta, right? We have sine inverse of cosine theta, which is equal to pi over 2 minus theta. If 0 is less than pi, which is less than pi, excuse me, if 0 is less than theta, which is less than pi, if theta is not in the domain, then we need to find another angle that has the same cosine as theta and does not belong to the restricted domain. We then subtract the angle from pi over 2. Similarly, sine theta is equal to a over c, which is equal to cosine pi over 2 minus theta. So cosine inverse of sine of theta is equal to pi over 2 minus theta if negative pi over 2 is less than or equal to theta, which is less than or equal to pi over 2. These are just the function co-function relationships presented in another way. So given functions of the form sine inverse of cosine of x and cosine inverse of sine of x, to evaluate them, if x is in 0 to pi, then sine inverse of cosine of x is equal to pi over 2 minus the x. If x is not in 0 to pi, then another angle y in 0 to pi such that cosine of y is equal to cosine of x, right? So sine inverse of cosine of x is equal to pi over 2 comma y, right? If x is in the negative pi over 2 to pi over 2 range, then the cosine inverse of sine of x is equal to pi over 2 minus x. If x is not in the negative pi over 2 to pi over 2 range, then we find another angle y in the negative pi over 2 to pi over 2, such that sine of y is equal to sine of x. So cosine inverse of sine of x is equal to pi over 2 minus y. Let's take a look. So we're evaluating the composition of an inverse, sine with a cosine. So let's evaluate sine inverse of cosine of 13 pi over 6. Right, we're going to do it by direct evaluation, by the method described previously. All right. So what I'm saying is we could always just do the inside first and then work our way outside. All right, let's take a look at how we got this done. So here we can directly evaluate the inside of the composition. So cosine of 13 pi over 6 is equal to cosine of pi over 6 plus 2 pi, right? Simplify it down, we get cosine of pi over 6, which is square root 3 over 2, right? Now we can evaluate the inverse function as we did before. So sine inverse, right, of square root 3 over 2 is equal to pi over 3. Right, so we have x is equal to 13 pi over 6, y is equal to pi over 6. And the sine inverse of cosine of 13 pi over 6, right, that's going to equal to pi over 2 minus pi over 6, which gives me pi over 3. All right. So evaluating compositions of the form f of g inverse of x. To evaluate composition of the form f of g inverse of x, where f and g are any two of the functions sine, cosine, or tangent, and x is any input of the domain g inverse, we have exact formulas such as sine of cosine inverse of x is equal to the square root of 1 minus x squared. When we need to use them, we can derive these formulas by using trigonometric relations between the angles and sides of the right triangle, together with the use of the Pythagorean relation between the lengths of the sides. We can use a Pythagorean identity sine squared plus cosine squared equals 1 to solve for one when given the other, right? We can also use the inverse trigonometric functions to find compositions, right, involving algebraic expressions. Now we'll be evaluating the composition of a sine with an inverse cosine. So find an exact value for sine of cosine inverse of 4/5. All right. Okay. So beginning with the inside, we can say that some angle such as theta is equal to cosine inverse of 4/5, which means that cosine theta is equal to 4/5. We're looking for sine theta, so we can use the Pythagorean identity like this. So sine squared plus cosine squared equals 1. We know that cosine inverse is going to give us the y value. I'm sorry, we know that cosine of theta is equal to 4/5, right? So plug in the 4/5 into the formula. Sine squared theta is equal, excuse me, sine squared theta plus 4/5 squared is equal to 1. We do a little math. We get sine of theta is equal to the square plus or minus the square root of 9/25, which equals to plus or minus 3/5. All right, so that'll be our answer for this. Two answers. Right. We want to go a little step further. Since theta equals cosine inverse of 4/5 is in quadrant 1, sine theta must be positive, so the solution is 3/5, right? We know that the inverse cosine always gives us an angle in the interval from 0 to pi. So we know that sine of that angle must be positive. Therefore, sine of cosine inverse of 4/5 is equal to sine of theta, which is equal to 3/5. And that's our final answer. Lots to think about with these. All right, so we'll call it at that. See y'all in class. Finish up your homework. Everything has been posted. All right, talk to y'all soon.